So I'd like to talk to you now about power in circuits, and this is getting back to our idea of fundamentals in circuit analysis. So first I'd like to talk about how energy is conserved in a circuit. Let's say that you have a simple circuit with a battery hooked to some kind of resistance. What happens in a battery is that chemical reactions occur that provide energy. As those chemical reactions take place, the elements within the battery start to be used up. So any energy that the battery supplies to the circuit is lost by that battery. The amount that the battery increases the electric potential energy of a system would be equal to the amount of charge it moves, Q, times the voltage of the battery, delta phi. And then of course the chemical energy of the battery decreases by that same amount. So if you look at the simple circuit diagram that we have here, as you move from point A to point B in the circuit, you can think of it as an increase in the potential energy of the charges within the circuit by an amount, Q delta phi. Now, the battery establishes a voltage, which then causes an electric field, which pushes our positive charges clockwise around our circuit, creating that current flow, I. As the charges move around the circuit, when they get to point C and then move through to point D, they move through the resistor. What happens to the charges in the resistor is that they make a lot of collisions. And in those collisions, the voltage drops as it moves across that resistor. Okay? The collisions cause the resistor to heat up. The energy conservation, the energy that was created by that battery, is dissipated within the resistor through the collisions, the inelastic collisions, and that causes heat. So the voltage then drops across the battery by an amount equal to Ohm's law in the circuit. So here that would be a voltage drop across the battery is equal to the current in the circuit times the resistor. So what happens is the energy created by the battery is dissipated eventually into internal energy in the resistor, or heat. Now we can talk about the power of a circuit. That's going to be the rate at which the system loses the potential energy as the charge passes through the resistor. Okay? You can also think of it as the energy that's provided by the battery, the rate that the battery provides energy, or you can think of it as the rate at which the internal energy of the resistor increases, or the heat of the resistor increases. Okay? It's important to remember that power is an energy per unit time. So whenever you're talking about power in a circuit, remember that it's an energy divided by a time. That makes the SI unit of power the watt, or 1 joule per second. In a circuit, we can write the power dissipated through various circuit elements in different ways. To derive this, let's think of it as the rate of energy lost by the battery, or provided by the battery. So that would be the power is equal to du dt, where U is the internal energy from the battery, the chemical energy that the battery is supplying. We can write that as the charge moved by the battery times the voltage of the battery, or Q delta phi. So this would be d dt of Q delta phi. Now, the voltage provided by the battery we'll consider to be a constant, so we can pull that out. And then we just have delta phi times dq dt. Well, dq dt is the definition of the current in our circuit, the rate of change of the movement of the charge, in other words, right? So that's I times delta phi. Now, if we apply Ohm's law, which is delta phi is equal to IR, we can rewrite this equation for the power, I delta phi, in any one of a more convenient form for the problem that we happen to be working. So that could be P is equal to I delta phi if you want the power supplied by a battery, or I squared R if you want the power dissipated in a resistor and you know the current, or delta phi squared over R if you know the voltage drop across your resistor, right, and you want to calculate the power that way. Always remember the units for the things that you're working in. Your current I will be in amps in SI, R is in ohms, omega it's symbolized, delta phi is in volts, or V, or power is in watts, W. Okay, let's talk a little bit about batteries and then work an example problem with power with them. So We often call the open terminal or the open circuit voltage of a battery the EMF, or the electromotive force, and we sometimes symbolize it by that curly uppercase E. So this is the maximum possible voltage that a battery can provide between its terminals. Remember that even though it's an electromotive force, it's not a force really. It's just an old-fashioned name for it. It's a voltage, okay? So in EMF, the units of EMF are volts. Batteries supply energy, all right? If the internal resistance of the battery were 0, then the terminal voltage of the battery will equal the EMF, but this is never true. In a real battery, there's always some kind of internal resistance R, and that's caused by the motion of charges through the electrolyte fundamentally, okay? If you want to calculate the terminal voltage of a battery, or what it would read if you hooked it up to an external load and then put your multimode probes right on either side of the battery, then you could write that as delta phi, which would be equal to the electromotive force epsilon, or capital curly face E, minus IR, where I is the current through the circuit and little r is the internal resistance of our battery. Remember, the EMF is the open circuit voltage. That would be the voltage if you had no current in the circuit. So if you took your multimode probes and you just hooked them up to a battery with nothing on it, you'd get very close to the EMF. That'll be the voltage that you read off the battery, what the manufacturer rates at. But the actual voltage between the terminals of the battery when you hook it up is going to depend upon the current in the circuit, and that depends upon what load you've hooked it up to, okay? That terminal voltage is also going to equal the voltage across your external resistance, or your load, okay? Let's do an example problem with this. Let's say that we have an 11 ohm load or an 11 ohm resistor connected across the battery. The battery has an EMF of 6 volts, but it's got an internal resistance of 1 ohm. So let's find the current in the circuit, the terminal voltage of the battery, the power delivered by the battery, the power delivered to the external resistor, the power dissipated by the internal resistance of the battery, and if the battery is rated at 150 amp hours, how much energy does it store? Okay, so in our little simple circuit diagram here, the EMF of our battery would be 6 volts, so capital E there would be equal to 6 volts. Lowercase r is the internal resistance of the battery, which we said was 1 ohm, and uppercase r is the external load, which is 11 ohms. Now, since the internal resistance of the battery and the external load are in series, the total equivalent resistance for our circuit would be 12 ohms. Now let's apply Ohm's law to find the current that the battery supplies. So delta phi is equal to IR. Delta phi here would be 6 volts, and then I times 12 ohms, which is the equivalent resistance of the internal and external resistances. When we solve for that, we get a current of 0.5 amps, half an amp. Now that we have the current, we can find the terminal voltage. That would be the EMF of the battery, 6 volts, minus the current times the internal resistance, 6 volts minus 0.5 amps times 1 ohm. That gives me 5.5 volts for the terminal voltage. I can now find the power delivered by the battery too. That would be I times delta phi, or 0.5 amps times 6 volts, which gives me 3 watts. Now the resistors are in series, so the current through them is the same as that delivered by the battery. If you want to write the equation for the power dissipated in an external resistor, and you know the current and the resistance, which we do, then you write P is equal to I squared R. That's 0.5 amps squared times 11 ohms for the external resistor, and that's a power dissipated in the external resistor of 2.75 watts. The power dissipated in the battery, in the internal resistance, would be I squared little r, or 0.5 amps squared times 1 ohm, which is 0.25 watts. Now how they rate batteries can be a little strange until you get used to it. What they said was that the battery is rated at 150 amp hours. So when they put the ratings down, oftentimes they cite it as a current times a time. Now, in order to calculate the total energy stored in the battery, remember that energy would be power times time. So if you want to use your equation for the power in circuits, you could say that power is equal to I delta phi, and then you would just multiply that times time to get the energy that the battery supplies. Okay? So here, P times T, which would be energy, would be equal to I times T times delta phi. Now, I times T they gave us, that's the battery rating of 150 amp hours. So I times T is 150 amp hours, and now we multiply that times delta phi, 6 volts. That would give us 900 watt hours. Remember, a watt is a joule per second. So we need to convert an hour into seconds and then multiply it times that in order to get our energy in SI units. 900 watt hours is an energy, no problem, but it's really not one that's too easy to look at because of the way that we think of the units. So if we want it in joules, we have to multiply 900 watts times 3600 seconds, and that gives us 3.24 times 10 to the 6th joules. Okay, I hope that clears some things up. If you have any questions, I'll see you in class.